Welcome to G Fun Facts Online. Today we are diving deep into the invisible machinery that powers the modern world. We often think of industry as something massive, towering oil refineries, sprawling pharmaceutical plants, and giant steel vats. But there is a silent revolution happening right now that flips this logic on its head. It is a revolution not of size, but of scale. We are moving from the macroscopic blending of bulk materials to the precise, deliberate manipulation of matter at its most fundamental limit, the atom. This is the era of nanocatalysis. For over a century, catalysis has been the workhorse of the global economy. Roughly 90% of all commercially produced chemical products involve catalysts. These are the substances that speed up chemical reactions without being consumed themselves. Traditionally, these catalysts have been blunt instruments. They work, but they are often inefficient, requiring immense heat, high pressure, and excess materials. Nanocatalysis changes this paradigm completely. By shrinking catalytic materials down to the nanometer scale, between 1 and 100 nanometers, scientists are unveiling unique quantum and surface properties that simply do not exist in the bulk form. Today, we are going to explore the atomic engineering behind these materials, how they are designed, synthesized, and deployed to rewrite the equations of manufacturing. To understand why this is such a breakthrough, we first have to discard our classical intuition of how materials behave. Take gold, for example. In our daily life, gold is chemically inert. A gold ring does not rust or tarnish. It is boring, chemically speaking. However, if you break that same gold down into particles smaller than 5 nanometers, it undergoes a dramatic transformation. It becomes a highly active oxidation catalyst, capable of converting carbon monoxide to carbon dioxide at temperatures as low as -70 degrees Celsius. This transformation is governed by two primary physical phenomena: the surface-to-volume ratio and quantum confinement. Let's look at the surface-to-volume ratio first. In a bulk material, like a gold bar, the vast majority of atoms are trapped inside the material. They are chemically dead because they cannot touch the reactants. But in a nanoparticle, this ratio flips. As the particle size decreases, the percentage of atoms residing on the surface increases exponentially. Let's look at the statistics. A particle with a diameter of 30 nanometers has roughly 5% of its atoms on the surface. If you reduce that size to just 3 nanometers, nearly 50% of the atoms are exposed. In the extreme case of single-atom catalysts, atom utilization reaches 100%. These surface atoms are what we call coordination unsaturated. They are frustrated. They lack neighbors on one side, leaving them with open coordination sites, or dangling bonds. These high-energy sites are desperate to stabilize themselves by bonding with reactant molecules, which significantly lowers the activation energy for chemical reactions. Beyond simple geometry, the electronic structure of the metal actually changes. This is where quantum size effects come into play. In bulk metals, electron energy levels form continuous bands. But in nanoparticles, these bands fragment into discrete energy levels. This leads to band gap widening, which alters the material's redox potentials. A critical concept here is the d-band center theory. The reactivity of transition metals is often dictated by the position of their d-band center relative to the Fermi level. Nanostructuring allows engineers to shift this d-band center. An upshift, moving closer to the Fermi level, typically strengthens the bond with adsorbates, while a downshift weakens it. Tuning this interaction is the essence of atomic engineering. It allows the catalyst to bind a reactant just strongly enough to break its bonds, but not so strongly that the product cannot leave. This balance is known as the Sabatier principle. Creating these atomic marvels requires a toolbox far more sophisticated than the crucibles and furnaces of the past. Modern nanocatalysis relies on a triad of disciplines: rational design, precision synthesis, and advanced characterization. It starts with rational design, the computational brain of the operation. Before a single beaker is touched, supercomputers model the catalyst using density functional theory, or DFT. Scientists use DFT to calculate adsorption energies for reaction intermediates. They plot these energies to create what are called volcano plots, which predict which metal combinations will sit at the peak of activity. Simulations also reveal that not all surface atoms are equal. Corner and edge atoms on a nanocrystal often exhibit activity orders of magnitude higher than terrace atoms. For example, in the water-gas shift reaction, it was discovered that platinum atoms at perimeter corner sites drive activity via a specific electronic structure effect, with a threshold occurring at an average nanoparticle size of roughly 1 to 1.5 nanometers. Once the ideal structure is simulated, it must be built using precision synthesis. One technique is atomic layer deposition, or ALD. This allows for the sequential layering of single atomic layers. It is used to create core shell structures, where a cheap metal core, like copper, is coated with a single monolayer of expensive platinum. This maximizes efficiency while minimizing cost. Another method is colloidal synthesis. By using surfactants or capping agents that bind selectively to specific crystal faces, chemists can force nanoparticles to grow into specific shapes, cubes, octahedra, or wires. This exposes only the most catalytically active crystal facets. There is also biogenic synthesis, a greener approach using microorganisms or plant extracts to reduce metal ions into nanoparticles, effectively acting as a natural bottom-up assembly line. Finally, we have characterization, or the eyes of the process. How do we know we built what we designed? We use tools like high-angle annular dark-field scanning transmission electron microscopy, or HAADF STEM. This technique uses electrons to image materials with sub-angstrom resolution. It can visualize individual heavy atoms, like platinum or gold, anchored on light supports, like carbon, appearing as bright stars in the night sky of the substrate. We also use X-ray absorption fine structure, or XAFS, which probes the oxidation state and local coordination environment. It tells engineers exactly how many oxygen or nitrogen atoms are holding a single metal atom in place. Perhaps the most cutting-edge frontier is operando spectroscopy. Catalysts are dynamic. They change shape during reactions. Operando techniques observe the catalyst while it is working. Researchers have actually watched copper nanocubes restructure into spongy, shapeless forms during carbon dioxide reduction, revealing that the reaction product itself drives the catalyst's evolution. Now, let's talk about the hierarchy of these materials. Not all nanocatalysts are created equal. First, we have metal nanoparticles. These are clusters of 10 to 1,000 atoms. They are the robust workhorses, used in things like hydrogenation reactions, but they suffer from polydispersity, meaning they come in varying sizes. Next, we have single-atom catalysts, or SACs. This is the ultimate limit of miniaturization. Isolated metal atoms are anchored individually onto a support. The advantage here is 100% atom efficiency. Every atom is an active site. Because every active site is identical, unlike a particle with messy corners and edges, SACs are incredibly selective, producing fewer byproducts. However, single atoms differ from bulk metals because they lack neighbors to share electrons with, often leaving them in a positive oxidation state. A recent innovation is heteronuclear dual-atom catalysts. This is where two different metal atoms are paired together, allowing for synergistic catalysis. One atom might adsorb reactant A, and the neighbor adsorbs reactant B, facilitating a reaction neither could perform alone. This theoretical elegance is translating into hard industrial gains across every major sector. Let's look at energy and the green hydrogen economy. The transition from fossil fuels to hydrogen relies entirely on catalysis. Traditional platinum electrolyzers are too expensive for global scale. Nanocatalysis offers a solution via single-atom platinum-carbon catalysts, which reduce platinum loading by 90%. Alternatively, we are seeing completely precious metal-free alternatives like nickel phosphide nanorods, which mimic the activity of hydrogenase enzymes. In fuel cells, specifically proton exchange membrane fuel cells, the bottleneck is the sluggish oxygen reduction reaction. Core shell nanocatalysts, with a platinum shell on a palladium or cobalt core, strain the crystal lattice of the platinum surface. This tunes the electronic binding energy of oxygen, boosting efficiency by 5 to 10 times compared to commercial catalysts. In the chemical industry, we're looking at green ammonia. Ammonia production for fertilizer consumes about 1 to 2% of the world's total energy via the Haber-Bosch process, which requires 400 degrees Celsius and 200 atmospheres of pressure. The nanotech solution involves ruthenium nanoclusters supported on electrodes. These materials act as electron pumps, pushing electrons into the chemically stubborn nitrogen triple bond, allowing ammonia synthesis at much lower pressures and temperatures. Even more radical is the move toward ambient condition electrochemical ammonia synthesis using iron-nitrogen-carbon single-atom catalysts, effectively turning electricity, air, and water directly into ammonia. Petroleum refining is another massive user of catalysts. Refineries need to crack heavy oil into gasoline and remove sulfur. Regulations now demand ultra-low sulfur diesel. Traditional catalysts struggle to remove sterically hindered sulfur molecules. Nano-stacked molybdenum disulfide slabs, engineered to expose more rim sites where the reaction occurs, are solving this. For heavy oil upgrading, nickel-tungsten nanoparticles supported on hierarchical zeolites allow massive asphalt-like molecules to enter the catalyst, get cracked, and exit as valuable diesel fuel. In the automotive sector, catalytic converters rely on platinum group metals to scrub pollutants. With prices skyrocketing, manufacturers are turning to single-atom rhodium on Syria zirconia supports. The single-atom dispersion prevents the rhodium from clumping at high exhaust temperatures, maintaining high activity with a fraction of the precious metal. They are also developing trapping nanocatalysts to hold pollutants during the cold start phase, releasing them only once the engine heats up. In pharmaceuticals, precision is key. Drug molecules are complex 3D structures. Left-handed and right-handed versions of the same molecule can have vastly different effects. Enantioselective nanocatalysis uses chiral ligands attached to the surface of palladium nanoparticles. These act as a glove, allowing only the correctly shaped molecule to dock and react. Furthermore, by building the catalyst on a magnetic iron oxide core, manufacturers can use a simple magnet to pull the expensive catalyst out of the reaction vat, ensuring zero metal contamination in the final drug. Of course, there are challenges. A major hurdle is stability. High surface energy means nanoparticles want to clump together, or sinter, to reduce their surface area, which kills their activity. Atomic engineers have developed ingenious ways to stop this. One method is strong metal support interaction, or SMSI. This is where the support material physically migrates over the metal particle, decorating or encapsulating it to hold it in place. Another method is nano-confinement, or the ship-in-a-bottle approach. Catalysts are synthesized inside the pores of mesoporous silica. The metal particle is physically trapped in a cage. It can rattle around and react, but it cannot escape to merge with other particles. We also have high-entropy alloys. By mixing 5 or more elements into a single nanoparticle, the high entropy of mixing stabilizes the solid solution. These cocktail catalysts are proving to be exceptionally stable and active. Looking to the future, the possibilities are expanding even further with AI and machine learning. The number of possible combinations of metals, supports, and shapes is infinite. Trial and error is too slow. Machine learning algorithms trained on databases of DFT calculations are now predicting optimal catalyst formulations. In one instance, an AI predicted a novel alloy for carbon dioxide reduction that humans had overlooked. We are also looking at photocatalysis and solar fuels. The holy grail is using sunlight directly to drive chemical reactions. Plasmonic gold nanoparticles are being developed to harvest visible light, acting as antennas to concentrate light energy and drive difficult reactions, like splitting water. Finally, sustainability drives the search for earth-abundant catalysts, replacing platinum and rhodium with iron, nickel, and copper. The shift to iron-nitrogen-carbon catalysts is the most promising route to making fuel cells cheap enough for mass adoption. Nanocatalysis represents the ultimate maturation of chemical engineering. It is the transition from the statistical average of the bulk to the deterministic precision of the atom. By mastering the behavior of matter at the nanoscale, we are unlocking pathways that were thermodynamically impossible or kinetically frozen in the macroscopic world. From turning exhaust fumes into clean air to synthesizing life-saving drugs with zero waste, the atomic engineering of nanocatalysts is the invisible engine driving our sustainable industrial future. Thanks for listening to Fun Facts Online.